Move It is a collaborative two-player activity where players move pentomino pieces from a starting position to a finishing position. One person in the group acts as the instructor, the other person is the computer who's just obedient. You can play it on a 10 by 10 grid, or if you want it more complicated, on a Cartesian plane. The advantage of the Cartesian plane is kids get to use the grid reference points to specify some things. So I've created a series of challenges at thinksquare.com.au/moveit. They start quite easy, and I drip feed these so kids can learn the concepts and have them explicitly taught bit by bit. So the first one is just translation. Now, as I said before, the advantage of this, if I want to translate this down here, I can look at the bottom right-hand corner of this and just say, I want you to move the bottom right-hand corner down to the point 7 minus 5. And that would require just one instruction to do that. However, generally what you're doing is kids are giving one instruction at a time. So if I wanted to get it there, I need to actually say, move this piece 10 units down because I want the top of it to be at -3. So 10 units down and then 7 units to the right. Now, if you just say move it 7 units, that's not specific enough. The computer doesn't know where to move it. It might move it back there. So you need to give a direction to each of your things. So that would be a solved puzzle. And I give kids a certain time limit to achieve this. The more pieces involved or the harder the puzzle, the more time I give. And you can adapt that to how your students are going during the activity. So we'll move to the second challenge. So the second challenge looks like this. After they've nailed the translation, we can do some rotation. So this might be, put it down here. And the only way they can solve this is by rotating. You can't make that piece look like it needs to without some sort of rotation or maybe flipping. But we're going to rotate 90 degrees. Again, we have to be specific because if we said anti-clockwise, it would mean this way. And if we said clockwise, it'll mean the other way. So we'll do a 90-degree rotation clockwise, and then we'll move 2 units to the right. Now, again, important, the instructor is not pointing and saying, like doing this, they need to just use verbal cues only, so it develops a shared understanding of the mathematical language. And again, you might not say rotate, you might say spin, and translate, you might say move. Sometimes you'll be able to perform what looks like a flip with a spin. So if we were trying to get this piece here, giving the instruction to flip vertically upward is one instruction way to do that. We could also say to rotate 180 degrees clockwise or anti-clockwise, and we'd end up like this to start with, and then we could move it 4 units upward. 1, 2, 3, 4, and that gets us to the same position, but we've used the second instruction. Now, the difference between flipping and reflecting is that flipping keeps one edge on the ground at all times. So if we're flipping vertically upward, it goes that way. If we're flipping horizontally to the right, it would go that way. Reflecting, imagine this is in a mirror, or the mirror is looking back at us here. So we're reflecting it in the x-axis, it would look like this. And the advantage of that is that if we had some annoying shape in the road, which I've designed puzzles later on to be exactly that, and we needed to get this piece here, we could do all the rotating and moving it around. We could go move to the right 20 units, move up 18 units, move back left, and flip it around. But we could just do one instruction, which is to reflect in the x-axis and get it there. So doing a reflection allows the shape to teleport. Otherwise, you can't move or pass over another shape or outside of the board when you're trying to solve these puzzles. And now we can get into some more complex puzzles. Like I said, they get tricky, and it's interesting watching such high-achieving grade 5 and 6s struggle with this, with both the mathematical language and just slowing down to work out what the best way to solve the problem was. There's often misunderstandings when you're just verbally communicating, and then also, you might do something and you go, oh, that was silly, now I've got to undo it. So this is the starting position. Generally, the starting positions are always on the corners and the other positions are here. Now, where would you start? What piece would you move first, knowing the finishing position? So if we move this, let's say we flipped it horizontally to the left. So that looks like what it needs to now. And then we move it 2, 4, 5, 6, 7 units across to the left, and then down 4 units. That'll get that where it needs to go. But then if we've moved this, somewhere like that, now this C piece is going to be very hard to get out. So we can't get it out unless we use a reflection of some sort. So that makes it difficult. So the way that you do it, since this needs to be up here, might be to move some other pieces out of the way and get them through first. But how you solve the problem will actually really affect the speed at which you can solve it. So there's the final solution, what it would look like if you just put them there.